The goal of this exercise is to use two 2.4 GHz RF transceiver modules to transmit data stored in the 25LC256 SPI bus serial EEPROM from one location to a receiving module where the data will be output to an 80-character LCD. The data to be transmitted will be preloaded onto the EEPROM by another program. That program collects 10 ADC values and sorts them into 4 categories represented by a 2-bit value. It is this 2-bit value that will be sorted and transmitted. This exercise is implemented using 2 programs, one for the transmitter, one for the receiver. The transmitter program takes the 2-bit data stored in the EEPROM and transfers it to 10 general-purpose register addresses. The data is retrieved from the GPR and then sent over the transceiver to the receiver module. The receiving program first takes the received data and stores it in its own GPR. As the receiver is waiting for data, a message waiting to receive data transmission is displayed on the LCD. Once it begins receiving the data, the message changes to collecting data. Once all the data is retrieved, a new message, sorting data samples, is displayed on the top line. On the lower line, each data sample is displayed in 5-second intervals according to the range in which it was assigned and in the order in which it was cataloged. After the 10th sample is displayed, the message "last data sample stored" appears, and the program ends. For this demonstration, I will be using 2 PIC trainer boards. The trainer board on the right has been configured as a transmitter. The one on the left has been configured as a receiver. Here is a closer look at the transmitter board. At lower left is the RF transceiver module. The IC just to the right is the serial EEPROM. Both devices use the serial SPI protocol. The PIC 16F877A has only one SPI port. To allow both devices to share the port, the breadboard is used as a parallel interface between the two devices and the port. 3 LEDs are used to monitor activity. The red LED on the far left indicates that data is being saved or transmitted. The 2 yellow LEDs on the right indicate the 2-bit binary value of the data being saved or transmitted. Looking at a close-up of the receiver board, we see an identical RF transceiver module to the one on the transmitter. This board has a short in one of the socket headers where the transceiver module is normally installed, so it has been mounted on the breadboard instead. According to the data sheet, the antenna should be ideally at least 1 inch away from any metallic structures. It has been mounted on a standoff to give it some clearance from the breadboard. The receiver also has the same activity LEDs as the transmitter module. On the far left, the red LED indicates the receiver is waiting for data from the transmitter, and the yellow LEDs represent the data being received. An 80-character LCD module displays a message indicating the stages of the program before finally displaying the received data sorted into 4 categories: high, medium, or low, or unknown, depending on the 2-bit value originally recorded by the ADC sorting program. Unlike the transmitter, there is no port sharing with the transceiver module or the LCD device. First, the data is loaded onto the EEPROM using a program created in a previous exercise. A multimeter shows the actual voltage from the potentiometer as it is adjusted. A new value is recorded and sorted every 5 seconds. The LCD shows the recorded ADC value in volts and the range it was sorted into. The sorted range is recorded as a 2-bit value. Binary 0 for unknown, 1 for low, 2 for medium, and 3 for high. With the data now loaded on the EEPROM, we can begin transmitting the data. I begin by turning on the receiving board first. The red LED indicates a wait for data, and also the LCD indicates waiting to receive data transmission. I will now start the transmitter. It is now reading data from the EEPROM and saving it on the PIC, general purpose memory. The two LEDs on the right represent the 2 bits of data stored on each byte. A binary 0, no LEDs, indicates sorted unknown. Binary 1, the far right LED, indicates the low range. 2, as seen there, indicates middle, and both LEDs lit. 3 indicates high. Now as you can see in the LED, we are collecting data samples. LCD, excuse me. Each time a data byte is transmitted, you'll see the activity light on the transmitter board along with its associated data light up. And you will immediately see it mimicked on the receiver board on the left. Okay, now we are done collecting the samples, and now we are in the stage where we are sorting the data back into its ranges. There we have sample 2 as medium, sample 3 as high. That's binary 3. Binary 0 sorted as unknown. Another binary 0 sorted as unknown. Binary 1 sorted as low. Another low. Binary 2 sorted as medium. Binary 0 sorted as unknown. And then we have a high. And that is our last data sample. We have completed the program. For this exercise, there are 2 issues that can cause trouble. First is on the transmission side. Since the EEPROM and transceiver share ports, they cannot be operating at the same time, so while one device is on, the other has to be turned off or cross-communication occurs. On the receiving side, I ran into problems using an existing LCD routine that was not written with the RF transceiver in mind. This has been a reliable LCD routine that has worked fine on its own. It did not work when used with the RF initialization routines. I later determined that the LCD display code used a short table for its initialization routine. Therefore, it needed to be in the first 100 addresses of program memory. The RF initialization routine uses over 100 addresses of program memory. The solution was to move the LCD initialization routine so it executed first.